Have you ever wondered why time flies when you're having fun but drags when you're bored? It's a fascinating conundrum, isn't it? How time, this constant entity, seems to twist and turn in response to our emotions and experiences. It's almost like time has a mind of its own, bending to our subjective perceptions. Now, let's push that thought a little further. What if time could stretch and shrink not just in our minds, but in reality too? And what if I told you it does? Enter Albert Einstein, the man who reshaped our understanding of the universe and time itself. His groundbreaking work, The Theory of Relativity, is composed of two parts: special relativity and general relativity. Special relativity, proposed in 1905, is built on two key principles. The first principle asserts the constancy of the speed of light. No matter how fast you're moving, light always travels at the same speed, a staggering 186,282 miles per second. The second principle is the equivalence of inertial frames. Simply put, the laws of physics remain the same irrespective of how or where you're moving. It's this second principle that lays the groundwork for general relativity, proposed a decade later in 1915. General relativity describes gravity not as a force, but as the curvature of spacetime caused by mass and energy. This theory leads to a fascinating phenomenon known as time dilation. So, what exactly is time dilation? It's a mind-boggling phenomenon predicted by Einstein's theory of relativity, where time appears to pass differently for observers in relative motion. Picture this: you're on a high-speed train and your friend is standing on the platform. As you wave goodbye and your train speeds away, your clocks start ticking differently. The faster you move relative to your friend, the slower your time appears to pass from their perspective. This is what we call time dilation due to relative motion. Quite a stretch from our everyday experiences, isn't it? But there's more. Time also dilates in strong gravitational fields. So, if you were to hang out near a black hole, your clock would tick slower compared to someone far away from it. Yes, gravity can actually stretch time. In essence, time dilation is a remarkable implication of Einstein's relativity, showing us that time is not as constant as we once thought. And this isn't just theoretical, we've tested it. Yes, we've actually tested time dilation. In the late 70s, Joseph Haefel and Richard Keating carried out an ingenious experiment, flying atomic clocks around the world on commercial airliners. The clocks aboard the planes, moving relative to those on the ground, ran slightly slower, confirming time dilation as predicted by Einstein's theory of relativity. But what does this mean for us in our everyday lives? Well, think about GPS satellites. These satellites whiz around Earth at high speeds and experience a different gravitational pull than devices on the ground. This leads to tiny time dilation effects. If not corrected, these effects could cause GPS coordinates to be off by several kilometers. So, our understanding and acknowledgement of time dilation is crucial for the accurate functioning of technologies like GPS. We've learned to account for the subtle shifts in time due to both relative motion and gravity. So next time you use GPS, remember that it works accurately because we account for time dilation. But time dilation isn't just about GPS. It takes us beyond to the edges of the known universe. Imagine the vicinity of a black hole where gravity is so intense that time itself stretches, slowing to a crawl. Now picture the expanding universe where cosmic time dilation causes the wavelength of light to stretch, redshifting distant galaxies. These phenomena challenge our conventional understanding of time and space. So, time, as it turns out, is far more flexible and fascinating than we often give it credit for.